All right, hello everyone. We're going to go through your two-way ANOVA assignment, and I have already downloaded the zip file with my data file and my R notebook, and with my answer sheet. And so we're going to go ahead and run through this. So you want to go ahead and put your name on your answer sheet up at the top, two-way ANOVA, and we're going to go through the assignment as it's outlined in our studio. Make this a little bit bigger. Okay. So I left this section about which Jamovi modules we're mostly using for the class. In case you don't have those installed yet, there's the ones that you should have installed. And we have our section with our steps for data preparation. And you want to go through and describe how you would accomplish each of these steps in the answer sheet. So first we're looking for data accuracy and make sure we know the levels of measurement for each variable and they're correct in the data set, looking for any typos or nonsensical data. Our categories all make sense. We need to correct any problems or decide not to use those data points or those individuals. Reverse code any items if needed, score the instruments if needed, and make sure you keep track of what you do so you can report it when you're reporting results, so you're transparent in your analysis. We'll also look for any missing data, if there's any outliers, and decide what to do with them, and look at statistical assumptions. Let's just take a peek at our answer sheet and see if there's things you need to fill in. So our variable data types, and since we're going to go ahead and look at that, why don't we go ahead and open our data set in Jamovi and go up here to the, I guess we'll call that the file menu, and we're looking for this data set that says goggles, and field describes this data set in his text in the two-way ANOVA chapter. So I'm not going to go over the variable types. You can skim through the chapter and see what this is. But we can look at the data. We have one variable that's called face type, and it has two categories, attractive and unattractive, and that's labeled as nominal, and I would leave that as that is. We have another variable called alcohol with placebo, low dose, and high dose, and since this is going, there's an order to this, I would go ahead and change that to ordinal. And then another continuous variable called attractiveness, and again, this is similar to last week's example where normally if I were judging what level of measurement this is, there's only a limited number of categories here. They're all integers, and they're rating the attractiveness of something. And since there's under 10 categories, I would actually call this an ordinal level of measurement. But for this example, we're going to leave that as continuous data, and you'll actually see these kinds of analyses done where this type of ordinal variable is used as a continuous outcome, and we do statistics on it, and there's a lot of debate in statistical circles whether that's appropriate or not. Be aware of that, but we're going to leave it there for the example that it is for our textbook. You want to go ahead and list the names of each of these variables and what the level of measurement is. Let's go ahead and look at some of our descriptive statistics. So this is a small data set. We only have 48 participants. And we can easily look through this and see that everything looks okay. But if this were a larger data set with more variables or more rows, then we would look at some of the descriptives. So just to show that, let's go ahead and split this by our alcohol and our phase type, and our attractiveness can go in the variables window. Go ahead and get frequency tables, and actually I'm going to leave those out. We're going to go ahead and get the mean and median for our attractiveness scores. And we want to look at, we'll go ahead and look at our standard deviation, skewness, and a normality test. And like I talked about before, when it comes to judging skewness, I usually like to use the skewness divided by the standard error of the skewness. And some of our numbers came up. We can see that we have 8 in each group according to our 2 categorical variables. No missing data. We have means for each of those groups, medians, standard deviations, minimums and maximums. Again, looking at skewness, if we look at the skewness divided by the standard error of the skewness, all these are less than 1. All those are 0.752. None of those would be greater than an absolute value of 2, so it seems our skewness is not overly large. And kurtosis isn't quite as important. Sometimes the normality test, the Shapiro-Wilk or the Kolmogorov-Smirnov, can be a little bit conservative and give a significant result when testing normality. So I do like to use that skewness divided by the standard error of the skewness, but none of our results are significant there either. And you can also look at plots, and box plot's kind of a nice thing to look at. Give that a minute to calculate, since we have quite a few categories that it's working on. And we can see here's our different groups, low dose and high dose. We don't see any outliers in any of these box plots, so everything looks pretty good for that. So I don't see any problems with this data set. There's no instruments to score, and you would just note if there's anything there. So statistical assumptions, we are working on a 2-way ANOVA. We did look at our normality, and we know that that is okay. We will look at homogeneity of variance when we run the test. And if any of our assumptions were violated, what are all our alternatives? And you'll note that there's no non-parametric 2-way ANOVA. And I don't think, I wonder what this robust, I'm not too familiar with. Well, it looks like we can put a couple factors in our robust ANOVA. And it does give us an interaction, so we could run a robust 2-way ANOVA if we had a problem with any of our assumptions. So that would be the alternative that we would look at. I do like to have you guys look at this StatCat in Jamovi for choosing the correct statistical test. So it's a great tool. Keeps you from having to memorize a whole lot of things. If you're doing statistics all the time, you'd get to know this pretty well. But we're looking at relationships, prediction, and group comparisons, and this is definitely group comparisons. And you'll see our independent variables. We can put more than one in there, so we're going to put alcohol and face type there. And under attractiveness, we can put that into our dependent variable box. And StatCat is nice enough to recommend a two-way ANOVA. And you'll see it gives us a little plot with our both of our categorical variables and the outcome variable. We can kind of see where the data points lie just to get a little bit familiar with it. And again, that's a nice tool. If you do click on these links, it does take you to a web page to describe a two-way ANOVA. I haven't read through that page yet, but I think it's a great option to get another description of what a two-way ANOVA is and how it works besides what you see in our textbook. So that's a nice tool. So again, for our assignment, I like to list out the full steps for null hypothesis significance testing. I think it's a good idea that you're aware of what the full process is every time you're doing one of these analyses. So normally you would decide upon a research question and your research hypotheses, and the research hypothesis can be different than the statistical hypotheses that we use later on, so I just want to make you aware of that, because these are stated in a lot more general terms. And we're not going to really go through this step because we already have a data set, but I do want you to be aware that this is part of the overall process. We would determine what data to collect and the level of measurement for each variable, and that StatCat's a useful tool for you can kind of think what you may collect and what the level of measurement might be, and you could use that to see what types of analyses may be possible. And if there's something that you want to find out and what you're thinking about isn't really working for the type of analysis you need to do, then you can play with what data you need to collect. So this is something that really ought to be planned out before you collect any data, just to save everybody time and heartache when they collect data and realize they can't really get what they want out of it. Determine your appropriate statistical analysis. Again, we kind of can look at that in step 3, and then collect data, which we already have a data set. So we're going to state our null and our alternative hypotheses. And this is a two-way ANOVA, and you know that we have two independent variables, and not surprisingly, each basically gets its own null and alternative hypothesis. So for our independent variables, the null would be there is no difference in the groups for independent variable 1, whatever that may be. And the alternative would be there is a difference between at least two of the groups. And the other independent variable would have the same null and alternative except for that variable. And as we know, we do have an interaction term that is part of our two-way ANOVA, and that's if variables for one independent variable behave differently for each level of the other independent variable. And so the null is going to be there is no interaction, and the alternative would be there is an interaction. So you're actually dealing with 3 sets of null and alternative hypotheses when you run a two-way ANOVA. This is a one-semester class. We're not going to get into ANOVAs with more than 2 variables, but beware they get more complex because you actually start having, if you have 3 independent variables, you're going to have a two-way interaction for each pairwise combination of the independent variables, and then you're going to have a three-way interaction that's possible. And I've never actually seen a higher ANOVA than that published. I've only read a couple three-way ANOVA studies. They're not very common. It's very complicated to interpret, and I've never seen a published one. I don't, I haven't read a lot of studies because I'm not currently doing research, but it's just not very common, so we're not going to bother looking at that very much in this level of a class. So we're going to keep our alpha equal 0.05 for the purpose of the examples in this course, and we're going to calculate our test statistics. So we're going to go ahead and go into Jamovi and see how to run our two-way ANOVA. So now we can go to Analyses, ANOVA, and we want to go to this regular ANOVA dialog. And our fixed factors are alcohol and phase type. And our dependent variable, our outcome variable, is attractiveness. And I'm going to go ahead and get partial eta squared. We talked about omega squared last time. Field, when reading through his chapter, says omega squared is less biased, but in my own statistics courses, partial eta squared is what SPSS would give, and that's what I've seen reported most often. So you can choose to report whichever effect size you would like. I think you could report omega as we did last semester in site field if anybody has any questions, and that should be perfectly acceptable. And it's not a big deal if we ask for omega. Also, you'll see partial eta squared and omega both come up here, or omega squared comes up and in our table. So when you look at the model, you'll see that we can specify what goes in here, but Jamovi defaults to how I would run this, with a main effect for each independent variable and an interaction effect for the pairwise combination of those two independent variables. So you'll also see that in our outcome table here, we have our sum of squares, our degrees of freedom, and our mean square values and F statistic for each of those effects. So if you haven't figured it out by now, when you're running a two-way ANOVA, it's in essence you're running three statistical tests, and you're going to look at the outcome for each of these as you go. Field in his text notes that there are different ways to calculate sum of squares, and we're going to leave it at the default. And if you want to, you can go look that up on Google. Field refers you to a online page if you want further discussion of what those are. Under assumption checks, we're going to go ahead and select all the options. We'll get our homogeneity variance test. Field really doesn't believe in a Levene's test for two-way ANOVAs. I think his arguments are pretty sound. So if you didn't report them and you just went with robust estimates, I think you'd be perfectly fine. But you could cite Field for why you may not do a Levene's test on two-way ANOVA. We did our Shapiro works for normality test, and I had added in a Kolmogorov-Smirnov test. Again, we didn't violate any normality things, and I did get a QQ plot just so that we can see it. This line basically is the normal line, and the data points should follow along that line if the data are normally distributed, and they pretty much are. So by all these measures, we are fine with our normality assumption. So the first time I kind of looked through this, I did not immediately see, we're not going to do anything with contrasts. We have to be a little choosy for a one semester course, and that's something we're going to skip over. If you're interested to learn more about contrasts, then you can read through it in Field and Google. But post-hoc tests, we're going to go ahead and ask for post-hoc tests. And Jamovi is kind of convenient because we can see our outcomes already. We can actually see that our p-values are less than 5. So you would want to run post-hoc tests to look at what's going on with these variables after the fact. In SPSS, you actually need to run this twice. You'll run it once and see if you have any significant results, and then you can either get your post-hoc tests, ask for them up front and not knowing, or go back through again and get the post-hoc test if you need to. And Jamovi makes that quite convenient to be able to pick that. For our class, go ahead and get post-hoc tests. So in the field text, no correction was called that LSD, least significant difference, which doesn't make any correction for doing multiple tests. Tukey is kind of a middle of the road option. It makes some correction. And Bonferroni is probably the most conservative option. And I have used Chaffee before. That is kind of middle of the road between Tukey and Bonferroni for how conservative it is when making corrections. So if you look on our post-hoc tests, we get our P, which is no correction at all. And then Tukey, you'll see that our p-value on no correction is 0.07. With Tukey, it's 0.178, so the p-value is higher, and this is being more conservative. And with Bonferroni, it's even higher than that. If we go ahead and click on Chaffee, you'll see that it lies between here, so they keep getting more conservative. And I am not actually sure what this home correction is, but I'd have to look it up. But you'll see it seems a little more liberal than Tukey is, and less conservative than the no correction. So I tend to wonder if that might be the correction for if homogeneity variance isn't the same, but don't quote me on that. I'm speculating without having to look it up one more time. But it's nice to see these different post-hoc statistical tests. I'd probably, go with Chaffee or Bonferroni and be conservative, but it wouldn't make a lot of difference here. You can go ahead and get a Cohen's d if you want to with your post-hoc test, and you'll see it just tacks on these things, and you'll see these effect sizes are all very small anyway. And these are looking at our alcohol variable, placebo compared with low dose, and placebo compared with high dose. And then you'll see our low dose and high dose. And you'll see our two placebo and high dose is significantly different, and our low dose and high dose is significantly different. And our post-hoc comparison on face type, we probably really didn't need that because there's only two groups. It'll be the same pretty much as the ANOVA, but its significance there is good to see that. So in our field text, one of the most useful things for interpreting these, and now that we've kind of picked a lot of options, before I do this last part, let's just talk a little bit about what we really care about in this ANOVA table, this two-way ANOVA table. So if we ran a one-way ANOVA, we would be looking at our alcohol variable and our attractiveness outcome variable on its own, or we would be looking at our face type variable and our attractiveness outcome on its own, and those would each be a one-way ANOVA. The real benefit of a two-way ANOVA is we can evaluate if there's an interaction between these two independent variables. If we just ran two one-way ANOVAs, one with each of these independent variables, we would have no idea if there's any difference in how these affect each other. That is the real strength of a two-way ANOVA, is allowing us to test this interaction between the two independent variables. And as such, I was taught, and I think this is the right way to go, and Field did not emphasize this quite as much, at least in the order that he interpreted his variables in the text for that chapter, is I think you should always, whenever you run a two-way ANOVA, the first thing you should look at is this interaction. And the question then becomes, is the interaction significant? And we see here that it is. And what that means is that the impact of one independent variable on the outcome variable is different for different levels of the other independent variable. And that's a pretty confusing thing to think about in your head. And so really the first thing I always check with a significant interaction is a plot. And it took me a little bit to figure out how to get this plot in Jamovi, but we can, and it's down here in the estimated marginal means section and our marginal means plots. So just to try and get a little orientation to how this works, I'm going to go ahead and take this alcohol variable and put it into this term 1 spot. And you'll see that we get a plot, and we can get error bars that are the confidence interval. I'll just leave that how it is. Well, let's go ahead and just say none for the moment. And you'll see here we have the means of our 3 groups for alcohol, placebo, low dose, and high dose, and the level for attractiveness. Now notice that this automatic scaling, this is only going from a little less than 5.2 up to 6.4. And so this makes this difference look huge. And in reality, this was on a scale of like 1 to 8. And so it's not as big as this scaling would make it appear. So you really have to be careful with your plots. Let's go ahead and hit this add a new term, and we will get a separate plot for face type. And now you'll see when our calculation is done, now we get face type. Again, there's only a little more than 1 point difference here, unattractive and attractive, and it's probably not that big of a difference as it appears there. But what we're really interested in is our interaction plot, and the question is, can we get that here in Jamovi? And the answer is yes, we can. And what I found the easiest to do was to add these variables one at a time. And in the book, he has alcohol along the x-axis, attractiveness along the y-axis, and different lines as the face type. And we're going to create that plot the same way. So I'm going to go down here, and we're going to add in alcohol first in our term 3. And there's our 3 variables along the x-axis. And now I'm going to add in face type right here below alcohol. And if I remember how to do this correctly, we should get a plot that looks very much like the interaction plot in Field's text. And there it is. Our scale's a little bit different. This is only about a 3-point difference, but you'll see we have our 3 alcohol groups, and our face type gets put in as separate lines. And we can see that for attractive face types, the dose of alcohol does not make a big difference in the rating. But for unattractive face types, the dose of alcohol makes a very big difference. And so for each of these 2 levels of the face type, there's quite a different impact of the independent variable of alcohol on attractiveness. So this is definitely an interaction, and this explains the significant interaction. And really, when the interaction is significant, that is the most important part of a two-way ANOVA analysis, and I would spend the most time describing what the patterns are here, that for attractive face types, that the dose of alcohol has very little impact on the attractiveness ratings, and for unattractive face types, that the dose of alcohol, as the dose gets higher, the attractiveness ratings get higher also. And then of secondary importance is the main effect from each of your independent variables. And so we can see that, so while all 3 of these are significant, the interaction is the thing that is of most importance. And Field, you really didn't get that unless you finish reading his interpretation. He went through and interpreted each of the main effects first, and then interpreted the interaction. And at the very bottom of his text in the interaction, in italics, he makes the point that that you really need to interpret a significant interaction, and that is the important part in the two-way ANOVA when the interaction is significant. And I think I would have changed his emphasis a little bit, and I actually would have started with the interaction and then moved on to the main effects. But that's some difference in maybe how we were educated on that. So if we look at our assignment answer sheet, you actually would have a null and alternative for each of those effects. So you're going to have a null and alternative for the main effect of alcohol. You're going to have a null and alternative for the main effect of attractiveness, and you're going to have a null and alternative for the interaction effect. So you'll need to add the extra lines in there for your answer sheet so you can state those null and alternative for each thing. It's basically like you're doing 3 statistical tests, the interaction and the 2 main effects. So there's going to be 3 nulls and 3 alternatives for those. Again, we're going to use alpha 0.05 for everything. And did you reject or fail to reject the null? And so you're going to have 3 of these. So for the interaction, we're going to say we reject the null, and we're going to make the conclusion that there is an interaction effect. And then you would go ahead and say, that the interaction is that for attractive faces, alcohol does not make a difference, and for unattractive faces, the amount of alcohol does make a difference in the rating. And then again, for the main effect of alcohol dose, you would say it is significant. You're going to reject the null, and you'll see, and what those numbers are going to be are the mean of our two other groups. And so you would basically be saying that the higher the dose of alcohol, the higher the attractiveness rating for our main effect of attractiveness, or main effect of face type. It was also significant, so you'd say you reject the null, and that that means that more attractive faces were rated higher, would be what that would mean in plain language. And any follow-up analyses, yes, we would do post hoc tests and an interaction analysis using an interaction plot, and we would state some of the things that we talked about, so you can go back and listen to some of what I just discussed earlier in the video if you didn't take note of that or remember what it is. So just like last week, our ANOVA, we reported our degrees of freedom and our F statistic, our p-value, and our effect size. We're going to report those same things for each of our effects. So if I go back up to the table here, so our degrees of freedom for our main effect of alcohol are going to be 2 and 42, and our F statistic is going to be 6.04, our p-value 0.005, and our partial eta squared 0.223. For our main effect of face type, our degrees of freedom are going to be 1 and 42, and F statistic of 15.58 with a p-value less than 0.001, and a partial eta squared of 0.27. And for our interaction effect, our degrees of freedom are going to be 2 and 42 with an F statistic of 8.51, p less than 0.001, and our partial eta of 0.288. So you'll pull all your information off of this ANOVA table, but I won't make you write out the full paragraph like Field has it, but pay attention to what he writes, because if you ever wrote up results, you'd want to pattern it pretty much similarly to how he did it. Go ahead and give any feedback, and you would save this output file and save your Jamovi OMV file, which I won't do here because we've done that in the past, so you can save that and then turn in your answer sheet and your OMV file for your assignment for this week. So that's your two-way ANOVA assignment, and I will see you guys in office hours. Have a good week.